If you've spent any time on YouTube or X in the last few weeks, you've probably seen the headline, "A quantum AI system just reduced data centers by 10,000 times. Engineers stunned. The end of the AI energy crisis. The death of the data center as we know it." It sounds incredible. It sounds like the kind of headline that should be on the front page of every newspaper on Earth. So here's the question we're going to answer today. Is it true? And I want to be upfront with you right at the top, because I think you deserve a straight answer before I take you anywhere else. No, not as stated. There's no verified, peer-reviewed, independently confirmed system that has reduced data center size, cost, or energy use by 10,000 times. That number does not exist in any scientific paper, any corporate earnings call, any government report, or any credible engineering benchmark. But, and this is the part that actually makes for a good story, there's something real underneath the hype. There's genuine, serious research happening right now that touches on quantum computing, artificial intelligence, and the future of data centers. It's just smaller, slower, and stranger than the headline wants you to believe. So in the next half hour, we're going to do three things. First, we're going to trace exactly where this 10,000x number came from, so you can see with your own eyes how a small, careful research result gets inflated into a viral myth. Second, we're going to walk through what quantum computing can actually do today, in the real world, inside real data centers, with real companies. And third, we're going to talk about what's coming next. The honest, unglamorous, but genuinely exciting timeline for when quantum computing might actually start changing how AI infrastructure works. Stick with me. Because the real story, it turns out, is more interesting than the fake one. It usually is. Part 1. Where did 10,000x actually come from? Let's start with some detective work. When a claim like this goes viral, it rarely comes out of nowhere. Usually, there's a kernel of real research sitting somewhere underneath. And somewhere between the lab and your For You page, that research gets stretched, twisted, and dramatized until it's unrecognizable. That's exactly what happened here. Buried in the noise, there is a real piece of quantum computing research. It's not flashy. It didn't make front page news anywhere serious, but it's real, and it's worth understanding, because it's the actual seed of everything you've been seeing. Here's the idea. Modern AI systems, the large language models, the recommendation engines, the massive neural networks that power everything from your search engine to your shopping app, have a problem that isn't really about raw computing power anymore. It's about memory. These systems rely on storing and processing enormous data sets, and as models get bigger, the pressure on data centers isn't just we need more processors. It's we need more places to put all this data and more energy to move it around. A group of researchers proposed a different way of handling that problem using quantum computing. Instead of loading an entire data set into memory before you start working with it, which is how classical computers generally operate, their method processes data incrementally. It takes in samples one at a time, applies quantum operations to each one, and then discards the raw data once it's been used. Over time, this builds up a compressed internal representation, a kind of quantum summary of the data that can then be used for machine learning tasks. Researchers gave this technique a name, quantum oracle sketching. Now, here's the important part, the part that never makes it into the viral headline. This is a theoretical and early experimental result. The researchers themselves estimated that you'd need a quantum computer with somewhere around 300 stable error-corrected qubits, what are called logical qubits, before this approach could reliably outperform classical computers on real tasks. And they noted that even a more modest machine, something in the range of 60 logical qubits, might start showing advantages on certain narrow data processing jobs used in AI. The catch? That 300 logical qubit machine doesn't exist yet. Not at Google, not at IBM, not at Microsoft, not anywhere. We are not there yet. This is a projection about what might be possible, grounded in real math. But it is not a machine humming away in a data center, somewhere reducing your cloud storage bill by 4 orders of magnitude. So how did a promising but early stage theoretical memory compression technique that might work once we build hardware we don't currently have turn into quantum AI system just reduced data centers by 10,000 times? Engineers are stunned? You already know the answer because you've watched this happen before with other stories. A real result gets picked up by content creators who are optimizing for clicks, not for accuracy. The nuance gets stripped away. The conditional language, could, might, under certain conditions, disappears. The impressive but bounded claim about a narrow technical bottleneck becomes a sweeping claim about the end of an entire industry. And a number gets attached to it because numbers make headlines feel scientific, even when the number itself doesn't map onto anything real. I want to be clear that I'm not saying the underlying researchers did anything wrong. Quite the opposite. This is exactly how good science should work. You take a real bottleneck, you propose a clever theoretical approach, You're honest about its limitations, and you publish it so other people can build on it. The distortion happens later, downstream, when that careful work gets fed into an attention economy that rewards exaggeration. So that's mystery number 1, solved. Now, let's talk about what's actually happening in the real world, because it turns out the true story of quantum computing and data centers is still genuinely fascinating. It's just a story about gradual, hybrid, and glamorous progress, not a single miracle breakthrough. Part 2, what quantum computers actually do in real data centers. Today, let's reset our expectations and look at what's really going on. For most of the last decade, quantum computing and AI data centers have been treated as two completely separate stories. Data centers were about gigawatts of electricity, strained power grids, and fights over who pays for new substations. Quantum computing was about physics labs, cryogenic refrigerators, and breakthroughs that always seemed to be exactly 10 years away, no matter what year you asked. That separation has started to break down. And the reason it's breaking down isn't because quantum computers suddenly became 1,000 times more powerful. It's because the infrastructure and the ambition finally lined up. AI's hunger for computing power has become so enormous that companies are now willing to explore even experimental, unproven technologies if there's a chance they might help. Here's what that actually looks like in practice. Microsoft has been developing a quantum processor specifically designed to fit into a standard server rack, the same kind of rack you'd find in any ordinary data center. According to a Microsoft executive overseeing the company's quantum efforts, the whole system draws about 30 kilowatts of power, and most of that energy isn't even going toward computation. It's going toward refrigeration, cooling the actual qubits down to a temperature just a fraction of a degree above absolute zero. Interestingly, the genuinely exotic part, the cold core where the quantum magic happens, is reportedly about the size of a soda can. Everything else around it runs at completely normal room temperature. It's a strange image, an almost sci-fi device at the center, wrapped in a mundane server room. IBM has gone even further into deployment. They have quantum computers physically installed at research institutions where they operate side by side with classical supercomputers, working on real scientific problems. At Riken, Japan's premier research institute, an IBM quantum computer sits right next to a supercomputer called Fugaku, and the two machines actually hand off parts of molecular simulation work between each other, the quantum machine handling certain calculations that are difficult for classical hardware, and Fugaku handling the rest. IBM's own CTO for quantum-centric supercomputing has described this as an evolution. The industry, in his words, is moving toward a data center model where CPUs, GPUs, and quantum processing units are actively co-located and expected to work together. Meanwhile, NVIDIA, a company whose entire modern identity is built around powering AI, recently launched a family of open-source AI models specifically designed to manage the errors that plague quantum hardware. Quantum computers are notoriously fragile. The qubits that do their computation are extremely sensitive to any kind of environmental noise, and correcting for those errors is one of the biggest unsolved engineering problems in the entire field. NVIDIA is pitching their new models as a step toward what they're calling quantum GPU supercomputing, essentially using classical AI to help make quantum computers more reliable, which is a wonderfully circular idea if you think about it. AI helping to stabilize the very quantum hardware that might, eventually, help train better AI. Now, why is any of this happening inside actual data centers, rather than staying in isolated physics labs the way it has for the last 20 years? The honest answer is because the infrastructure is already there. Some of the people who study this space describe quantum computing as the next layer in a kind of technological layer cake that data centers have been building for decades. First corporate IT systems, then telecommunications, then mobile and cloud computing, then the artificial intelligence boom, and now cautiously, quantum computing stacking on top. But here's the thing I want you to really sit with, because it's the single most important corrective to the viral hype. Virtually everyone who actually works in this field, when asked directly, pushes back hard on the idea that quantum computing is about to replace or shrink data centers the way the headline suggests. One expert, an IEE member who teaches quantum-adjacent business courses, put it about as plainly as you can put it. Think of quantum computers as different types of computers, built for different use cases, not faster general-purpose replacements for the servers you already have. Different tools for different jobs. And IBM's own quantum computing CTO said something that should really stick with you. One thing quantum computing is not going to do, in his words, is make the data center energy crisis go away. Let that sink in for a second, because it directly contradicts the entire premise of the viral headline. The people building this technology, the people closest to it, the people who would have every incentive to hype it up if they thought they could get away with it, are telling us clearly this is not going to shrink the AI energy crisis by 10,000 times. It's not going to shrink it by 100 times. It's going to add pockets of specialized capability into a system that will otherwise keep growing because of AI, not because of quantum computing. So what actually is quantum good at, if it's not a magic shrink ray for data centers? It's good at a narrow, specific category of problems that classical computers genuinely struggle with. Designing new battery chemistries, modeling how molecules interact with each other, which matters enormously for drug discovery. Building more efficient photovoltaic cells for solar power, optimizing complex financial portfolios, and pricing financial derivatives in ways that can give firms a real edge. These are the problems where the strange properties of quantum mechanics, superposition, entanglement, interference, actually give you a computational advantage over ordinary bits. There's also a genuinely serious side to this technology that has nothing to do with making things smaller or more efficient, and everything to do with risk. A powerful enough quantum computer could, in principle, break the encryption methods that currently secure most of the internet. One major financial analysis described this as potentially the biggest risk associated with the entire technology, warning that companies will need to start implementing new quantum-resistant encryption techniques well before quantum computers are powerful enough to actually pose that threat. That's not a shrinking data center story. That's a completely different story, a security story, and it's arguably more urgent and more consequential than anything about data center size. Part 3. The real numbers. The real timeline. Let's ground ourselves with some actual figures, because vague optimism is just as unhelpful as vague panic. One widely cited estimate suggests that quantum computing could influence as much as 10% of overall data center demand over the next decade. Compare that to the explosive growth already happening because of conventional AI. One projection has AI's own share of the data center market roughly doubling to around 30% within just a few years. In other words, even in an optimistic scenario, quantum computing's near-term footprint on this industry is expected to be a fraction of what plain old AI is already doing, not a replacement for it. There's also a cost and complexity reality that never makes it into 3-minute viral videos. Building even an early commercial-scale quantum computer is currently estimated to potentially cost tens of millions of dollars. One detailed industry analysis described the field as being close to completing a machine at that price point, capable of solving in a couple of minutes a problem that would take an ordinary supercomputer roughly 10,000 years. That's a genuinely staggering number, and it's real. But notice what it's describing. It's describing raw computational speed on one very specific, very narrow type of mathematical problem. It is not describing a reduction in data center footprint, energy consumption, or physical infrastructure across the board. Speed on a narrow problem and size reduction across an entire industry are two completely different claims, and the viral headline quietly swaps one for the other. As for timing, the people actually building this hardware tend to be fairly consistent and fairly modest in their predictions. Several industry voices point to the years around 2028 to 2030 as the point when we might see quantum computers doing commercially meaningful work, meaning calculations that classical machines genuinely cannot perform at all, not just perform more slowly. One prediction even suggested that by 2029 we could see machines whose value is undeniable in that sense. That's not a headline about right now. That's a headline about the end of this decade at the earliest, for even the first wave of clearly commercial value. And there's a deeper structural point worth making here, because it explains why quantum computing is unlikely to ever simply replace classical data centers, even in the long run. Quantum computers are extraordinarily good at a narrow set of specialized problems. They are not good general-purpose replacements for the servers that run your email, stream your videos, host your websites, or do the ordinary bulk of AI training and inference that businesses rely on every day. The emerging model, the one that essentially everyone building this technology seems to agree on, is a hybrid one. Classical CPUs handling everyday computing, GPUs handling the parallel processing that modern AI depends on, and quantum processing units handling a narrow slice of specialized problems, all sitting inside the same facility, handing work back and forth between each other as needed. That's a genuinely exciting vision of the future. It's just not the vision the viral headline is selling you. It's not one quantum breakthrough replaces the entire data center industry. It's a new specialized tool slowly gets added to an existing growing toolkit. There's also meaningful work happening that's a bit more grounded and closer to today, worth mentioning, so this doesn't sound purely speculative. Some data center operators are already using ordinary non-quantum AI to meaningfully cut costs right now. One well-known example, an AI system used to dynamically adjust cooling systems in real time, achieved roughly a 40% reduction in cooling energy costs at certain facilities. That's not quantum computing. That's classical machine learning, deployed today, delivering real, measurable, and glamorous efficiency gains. It's a good reminder that meaningful progress in this industry doesn't always need a dramatic headline attached to it. Part 4. Why does this kind of story keep happening? I think it's worth pausing here and asking a slightly bigger question. Why does this pattern keep repeating itself? Why do we keep seeing real, careful, incremental scientific progress get transformed into breathless, implausible viral claims? Part of the answer is just basic economics of attention. A headline that says, researchers propose theoretical method that might reduce quantum memory requirements once we build hardware that doesn't exist yet under specific conditions, is accurate, but nobody clicks on it. A headline that says, quantum AI just destroyed the data center industry gets millions of views. The incentive structure of online content rewards confidence and drama, not precision and hedging. And when the topic is something as genuinely complex and unintuitive as quantum mechanics, there's an added advantage for exaggerators. Almost nobody in the audience has the background to immediately spot the distortion. Quantum computing sounds like magic to most people, which makes it the perfect subject for magical claims. Part of the answer is also that there's a real legitimate story sitting right next to the fake one. And that legitimate story lends the fake one a kind of borrowed credibility. It's true that major companies like Microsoft, IBM, Google, and NVIDIA are seriously investing in quantum computing. It's true that quantum processors are being installed inside real data centers today. It's true that serious financial analysts are writing 100-page reports about this industry. All of that is real, and all of that gets cited, sometimes accurately and sometimes not, to prop up much bigger and much less accurate claims layered on top. So the lesson here isn't ignore anything you hear about quantum computing. The lesson is closer to when you see a specific dramatic number attached to a complex scientific field, 10,000 times, 1,000 times overnight, treat that specific number as the thing most likely to have been distorted, even if the general direction of the story turns out to be true. Ask where the number came from. Ask whether the underlying research actually claims that number, or whether the number appeared somewhere downstream, added by someone with an incentive to make the story bigger than it is. Part 5. What should you actually take away from all this? Let's bring this all the way back down to something practical, because I don't want to leave you with just the internet lied to you again. That's true, but it's not that useful on its own. Here's what I think is actually worth remembering. First, quantum computing is real, it is progressing, and it is genuinely being integrated into data center environments today, not in some distant hypothetical future. That part of the story deserves your attention and, frankly, your excitement. Companies like Microsoft and IBM aren't running publicity stunts here. They're doing serious infrastructure engineering right now to fit quantum processors into existing facilities. Second, quantum computing is not a general-purpose replacement for the classical computing that already powers data centers, and it's not on track to become one anytime soon, if ever. It excels at a narrow category of specialized problems: chemistry, material science, certain kinds of optimization, and financial modeling. And the honest experts in this field are the first ones to tell you that. Third, the specific claim in that viral headline, a 10,000 times reduction in data centers thanks to quantum AI, does not correspond to any real, verified, deployed system. The closest real thing is an early theoretical research proposal about compressing AI memory requirements using quantum techniques, which requires hardware that doesn't exist yet to even test at meaningful scale. Fourth, the realistic timeline for quantum computing to have a clearly commercial, undeniable impact is generally described as sometime around the end of this decade, into the early 2030s. And even then, most serious estimates put its overall share of data center demand in the range of maybe 10% over the following decade, layered alongside classical infrastructure, not replacing it. And fifth, maybe the most useful takeaway of all, real technological progress in this field looks a lot less dramatic day to day than the viral version of it. It looks like a company fitting a refrigerated processor into a standard server rack. It looks like two very different types of computers, sitting side by side in a lab in Japan, handing pieces of a problem back and forth. It looks like researchers publishing a careful paper with a lot of caveats, estimating what might be possible with hardware that's still years away. It looks, in other words, like ordinary science, slow, careful, and honest about its own limitations. That's not as exciting as engineers are stunned. But it has one major advantage over the viral version. It's actually true, and it will still be true next year, and the year after that, when the theatrical headline has long since been forgotten and replaced by the next one. So the next time you see a headline promising an instant world-changing breakthrough in quantum computing, in AI, in any fast-moving technical field, here's a simple habit worth building. Pause for just a moment before you share it. Ask yourself where that specific number could possibly have come from. Ask whether the people who are actually building this technology, the engineers and researchers with their names on the real papers, are making that same claim themselves, in their own words, without a dramatic thumbnail attached. Most of the time you'll find what we found today. A real, interesting, worthwhile piece of progress, buried underneath a number that somebody invented to make it sound bigger than it is. The truth is almost always more modest than the headline. But if you actually look closely, it's usually just as interesting, sometimes more so, because it's the kind of interesting that's still going to be true tomorrow. Thanks for watching. If you want, next time we can go deeper into exactly how quantum error correction works, or why breaking modern encryption is considered quantum computing's biggest near-term risk rather than its biggest near-term benefit. Let me know which one you'd rather see next.